Okay, so I recently joined SiFive, but this work is essentially based on academic work I've done while I was in Okay, so TAGE was introduced in 2006. You know, I guess that most of you knows how TAGE is working. It uses multiple tag table. It uses geometric history lengths for indexing the different table. The longest matching table provides the prediction, with an exception when the prediction counter is weak. And you have a selection between the alternate prediction and the prediction, the longest matching prediction. Okay. So that was in 2006. It won the second championship. After that, I derived the TAGE-SC predictor. Essentially, that was the same structure in the three following championship. So main predictor, TAGE predictor, that you take the prediction, the confidence, some information flowing from the TAGE predictor. You take global history, local history, IMLI counters, and you index tables in what I call a statistical corrector, which is just a neural predictor. It provides you a prediction to grab the rest of that you use a risk predictor and finally get the prediction. So it was as it was designed for winning a championship, it is not directly implementable in hardware. Okay, too many tables in the TAGE components, too many tables in the statistical corrector component. Use of local history, and it's a nightmare to manage speculative local history. And just a huge latence, because you have the TAGE latence, then you have the neural predictor latency. To the best of my knowledge, there's no official implementation of this TAGE-SC predictor. And I added recently official. So, just before joining SiFive, I released this design where you have the TAGE predictor in parallel with the statistical corrector. You compute speculatively for prediction with the statistical predictor, and you use the prediction that flows out from the TAGE predictor to select the correct prediction. And this one has correct latency. It has not too many tables. So I will say, if you want to see how you could implement TAGE-SC, look at my report that I released just before joining SiFive. So in this report, I revisited the alternate prediction. In fact, computing the alternate prediction would be a critical path. But if you use HC-pred, which is the longest eating not weak entry, this could be computed at the same time as the prediction, so it will not become a critical path. Okay, this is illustrated here. So now we're in a competition. You have to come with something reasonably good. So I took the CBP2016 TAGE-SC code, I ignored the loop predictor, and insert the innovation from the TAGE-SC, the realistic TAGE-SC that I proposed. So some tricks on replacement, policy, re-engineering, and that comes from better understanding of the IMLI component, use of IC-pred instead of alt-pred, and as I was wanting to compete, I used the dirty tricks of CBP 2016, so huge numbers of TAGE tables. Nobody will implement that. Huge numbers in the statistical corrector of tables in the statistical corrector. Nobody will implement that, and use of local history. That's not something that we want to do all. So some optimization of on TAGE. So the treasures numbers of tables, 28 historic. Come on. Global tag table sharing. Come on. Something that I like a lot is two-way student perspective structures on each bank. By the way, I invented student perspective. We use a large number of tag bits because we have a huge budget. I remark that geometric series is not that optimal. It seems better to concentrate these storylines in the middle of the spectrum, so I did that. So, yeah, the list of optimization on allocation replacement, because replacement is not on the critical path in TAGE, and that's where we can do optimization that are a little bit tricky. Okay, just the list. So with TAGE only, we were, and 76% of the storage budget, we were adding to 3.781 MPI. Now, let us have a look at the SC component. We, as I already said, I ignore the loop predictor. So, when you use the SC component, the first thing that you want is that it captures correctly what is coming out from the TAGE component. So, with only 3 tables and a few others that I added, but they're not important. We are reducing the misprediction rate by 4%, which is great. Now, we can use other information, global path related information. So, globally, the geometric history length predictor that I proposed for the first I use also backward taken history, forward taken history, and the history of the 256 bytes that we are touching. And with this, we reduce the misprediction rate by something like 2.5% over the previous one. So, for those of you that do not know what is IMLI, IMLI is a concept they introduced at micro 10 years ago. The innermost loop iteration number, and that comes from the fact that when you have a loop, sometimes inner branches in this loop are correlated with the loop iteration number. So we have shown that this was working great on CBP 2014 traces, but it was not that great on CBP 2016 traces. So that's an innovation that I introduced. Oh, no, sorry. So in this, we count the number of consecutive taken branches within the same region, a region being essentially a cache line in this case. And you see that we captured here the iterations that come from 3 different branches. And in fact, we are able to monitor the number of iterations in a loop with multiple exits. Okay, so this loop has 2 exits. Or monitor the number of iterations in loop nest. Okay, and the region is 64 bytes, but it could be 256 bytes or 4 bytes. Sorry. No. What is the mess? Okay. Of course, you may have a problem when you are at this frontier. So I also introduced another form of IMLI, which is the target IMLI. So which is you have your target in the same region. And essentially, it captures the same phenomena as the first one, but it adds some coverage. Let's go. Yeah. So with this, we reduce the misprediction rate by 1.5%. Essentially, why I do not include the loop predictor. Essentially, we're covering also loops, most loops. So it's not, there's no benefit in adding a loop predictor in terms of. Now, something that I hate. Okay, local history components. So to win or to compete in a championship on branch prediction, you have to integrate that. And I did. Okay, 4 types of different local history, a total of 14 different tables in using local history, and that reduced by the misprediction by 3%, and that's my final number. Okay. Now, if you consider effective implementation, apart the outrageous numbers of tables that I told before, to recover on a misprediction, you have to be able to recover. So you have to checkpoint some information associated with each branch. For TAGE, it's okay. It will be 13-bit pointer, so okay. For the global path related SC components, in this you will need 86 bits of global history. In fact, in a realistic design, you will need much less. For the SC components related with IMLI, in this design you would need 104 bits, which is a little bit large, but in fact, I would say on a realistic design, you would need only half of 6. And of course, for local history, just ignore it. Okay. 5K bits to be checkpointed on each branch. I am not aware of any realistic management of speculative history for a processor where you can have about 100 branches in flight at the same time. So, summary. I presented TAGE-SC for CBP2025, got 2% of reduction versus the scale 192 kilobyte TAGE-SC from the organizer. My own scaling was worse than theirs, which is weird. So, this is a limit study. Don't try to implement it directly in hardware. For realistic hardware TAGE-SC implementation, look at this report. Okay, so I would say, and Rami told that also, we need new ideas. So maybe it will come from other information for vectors for SC. I have understood that there are some radically new approaches that will be presented. So I'm happy, and maybe with this CBP we will make a lot of progress. Thank you.
Yeah, we're short on time, so we can probably switch. No, probably time for questions.